Good morning, everyone. My name is Anders. Good morning. My name is Anders Heilsberg, and I'm here to talk about our 10x faster TypeScript project, the project to port the TypeScript toolset to native code. First, want to thank you all for showing up early on the last day of the show. I appreciate it. And after the presentation, I'll hopefully have some time left over also to do some Q&A. There's a microphone there. A little bit of history. The first ideas for TypeScript are almost 15 years old today. We started prototyping in 2010, towards the end of the year. Had our first release in 2012, and have been at work ever since. Open source from the beginning, and TypeScript has always been about teasing out the good parts of JavaScript and building a scalable developer experience by adding a static type system and then using that to enable great tooling built on top. You're familiar with this, I'm sure, but just it's amazing the growth that we've seen. It's surprised. If you had asked me 10 years ago, would we ever get to this point, I would have said no. But here we are. TypeScript is now the number 3 language on GitHub. If you put together TypeScript and JavaScript, they actually outnumber all other languages, even Python. And today, TypeScript and JavaScript have basically gotten commingled, right? And we know that 75% of the world's professional developers use TypeScript to write their JavaScript apps. So that's, of course, been super motivating for us as a team. And throughout the project, we've been open source. We moved to GitHub in 2014, so more than 10 years ago. We have had over 50 releases of the product since. We're on a 3-month cadence. Lots of community involvement. We take a lot of PRs from the community, and generally it's a very vibrant project. Now, from day one, we were hosted in ourselves, so we sort of bootstrapped, and so we've basically been writing a compiler in JavaScript for more than 10 years now, a compiler and a language service, which is something I would have totally forsworn if you had asked me if I'd be doing that for a decade. But it's actually been really good for us to be hosted in ourselves, because we have learned from use exactly what's good and what's bad about JavaScript. We've learned a lot about how to fit a type system on top of a language that has a bunch of constructs that don't actually exist in other programming languages. But it also comes with some challenges. JavaScript was never conceived to be a high-performance runtime for compute-intensive workloads. And that is what a compiler is. JavaScript comes with some overhead. It's JIT compiled. It has an expensive object model. And it has some pretty severe restrictions around concurrency. There's no support for shared memory concurrency, which means it's really hard to, in a single program, to take advantage of multiple CPUs. Furthermore, over time, the TypeScript compiler has gotten more complex. We've added a lot of features. In fact, I went back and grabbed TypeScript 1.5 and used it to compile itself, and then used today's compiler to compile. And the current compiler runs only at 50% of the speed of that original compiler, because we do a lot more. We've introduced concepts like union types and control flow narrowing and all sorts of super fancy stuff, that helps the developer experience, but it takes time to compute that stuff, and so compiles go slower. And at the same time, projects are getting bigger and bigger all the time. Nothing ever gets smaller, right? If you'd asked us 10 years ago, would people be writing million-line projects in TypeScript? We go, no, that's crazy. There must be a configuration error. Why are you compiling this many lines of code? And now That's par for the course. Now, Visual Studio Code is 1.5 million lines of code. There are many other open source projects, companies with 5 million lines of code. We have internal repos with 15 million lines of TypeScript. It's crazy. So all of that also means that the most commonly reported issue we hear is out of memory. And a lot of tools have gone native at this point. You know, if you use ESBuild or SWC, for example, and we've heard from the community, gosh, when are you going to move to native code? It's going to be twice as fast. It's going to be 20 times. It's going to be infinite times faster. I mean, it's like we've heard all sorts of numbers. There have been several attempts by developers in the community to try and port or write a new TypeScript compiler, but none of them have succeeded. But by fall of last year or August, we sort of decided, okay, it's time to get some real data on this problem. And so we started prototyping. What would it look like to move to native code? And we obviously had some requirements. We wanted, we needed to pick a language to move to because it wasn't going to be JavaScript. We had some requirements like we wanted optimized code on all major platforms. We wanted a language that would allow us to preserve the structure of our code base. Our code base is written in a certain style that, you know, and we knew from day one that we wanted to port. We're not going to write a new compiler. We wanted to preserve the semantics and basically give you a drop-in replacement for the existing TypeScript toolset, except in native code, but with exactly the same behavior. We wanted a language that would give us flexible data layout. JavaScript doesn't have structs. Everything is an object allocation in a heap, you know, even if you have a bunch of small little objects. And we wanted something that would allow us to just put them in an array and, and not pay a bunch of overhead. We obviously wanted a language that permits cyclic graphs, because all of our data structures are like trees with parent pointers and, you know. We wanted automatic memory management or garbage collection, because that's what our existing code assumes. And we knew that we wanted access to shared memory concurrency, because that is how we're going to make the compiler faster. We looked at 3 alternatives: Rust, Go, and C#. And each of them have characteristics that worked and that didn't. If we start with Rust, Rust does not have automatic memory management. And it also forbids cyclic data structures. And those are 2 really, really hard issues to work around. And for that reason, it just wasn't going to be feasible to port to Rust. It might have been feasible to rewrite in Rust, but that's not what we wanted to do. C# is definitely a possible contender, but it is a higher level language. It is object-oriented, where our code base is actually written more in a procedural style with just functions and data structures. We don't have any classes at all in the compiler. C# also doesn't have a native code generation story that is quite as mature as some of these other programming languages. And then we looked at Go. And personally, I hadn't really written any Go before last August. I'd heard about the language and I was intrigued by it, and you know, some of the things that worked for us and why we picked Go is that it has great support for native code, and it's more than 10 years old. It's on all major platforms, highly optimized stuff. It is a procedural language. It doesn't actually have classes. There's no inheritance or subtyping in Go. It's just functions and data structures. There are interfaces, but it does support first-class functions and the ability to have functions within functions and close over outer state, which is something we do a lot in our code base because that's very popular in JavaScript. It has great support for controlling your data layout, structs, pointers, what have you, and it has excellent support for concurrency. And so we started prototyping in Go in August of last year. The first thing was to port the scanner and the parser. And quickly, we discovered that we could realize a 10x gain. And that kind of got us going, hey, I mean, 10x is like, you can't argue with 10x, right? And so by October, we committed the entire team to actually porting the code. And I'm going to talk about the status today, but first let me switch to this machine here, and then let me just, for some comparison, start by compiling this project here. This is the Visual Studio Code projects, 1.5 million lines of code, and I'm just going to compile it and type check it, and we'll see how long that takes, and then we can talk while that's going. So today we have 150,000 out of, say, roughly 250,000 lines of code ported. The type checker is complete, and I mean complete. It literally is the same type checker, and it supports JSX as well. JSDoc is almost complete. We're making a few changes there because our JavaScript and JSDoc support had a bunch of stuff in there that people don't really use anymore, that goes back 10 years. Our emitter is in process. We can erase types, and we can turn modules into CommonJS and whatever, but we don't have declaration file emit yet. That's in flight. We don't have composite projects. We only compile single projects currently. And we're building an LSP-based language service. TypeScript predates the language server protocol, and we're switching now to LSP, which also should make our language server, our language service, more usable in all sorts of other environment. And we're doing some API prototyping. Obviously, because we were written in JavaScript, the compiler was an open book. You could call any function in a compiler, and people did, and they did all sorts of interesting stuff with it, which is fantastic. But we're sort of going from every function in a compiler being available to 0 functions in the compiler being available because it's an exe. And what we're building here is an IPC-based API that allows other languages to call services in the compiler by doing inter-process communication. All right, so here we go. Let's go back and take a look at our compile here, and you'll see that it takes about a minute to compile Visual Studio Code. Now let me try with a new compiler and ask it for diagnostics as well. And there you go, 5.6 seconds. So thank you. So more than 10 times faster. And other than that, you see the diagnostics that get spat out are quite similar. But one notable difference is we had to add an extra decimal to the timings because we go 10 times faster, right? Yeah, so let me try to go back here. All right. Here are some project build times, current versus native. And you can see, we've tried it now on many different code bases, and it pretty much holds up. We're 10x. Half of our gain we get from being in native, and the other half we get from concurrency. And I'll talk about how all of that is put together. One recent experiment we did was compiling a very large, Daniel gave me the screenshot, a very large code base, 15 million line code base that we have inside Microsoft. It's broken into multiple projects. We turned it into one big project and fed it into a 32-core, 128 gig build machine in the cloud. And it compiles in, 50 seconds, I think, which is insanity. I mean, the old compiler couldn't even do this before. And you notice on this CPU monitor here, we're keeping all 32 cores going at full throttle. Previously, because of JavaScript's restriction, you would see one bar here. And we would leave a lot on the table, right? And now we can finally harness all that power. We're already seeing a lot of use of this. I mean, we've obviously been open source from day one, and you can clone and build the repo yourself. The company Lattice, they have about 5 million lines of code. They've switched entirely to using the native compiler and are very, very happy and are seeing, an 85% reduction in build times. This is where we host the repo. All of it is open source, and you can go clone it and build it yourself. And I'm going to talk about a little later at the end of my talk about how we're going to make it much easier for you to get builds of the compiler and the language service. Now I'm going to spend a bit of time on how did we do this. This is obviously not a simple undertaking. As I mentioned, we knew from day one that we wanted to port, not rewrite. We wanted to preserve the exact semantics. We wanted to be able to open the drawer, take out the old compiler, put in the native compiler, close the drawer, and no one would know except it goes 10 times faster. That was the marching orders, basically. Now, for prototyping, we ported the scanner and the parser by hand. It took about 8 weeks. That was from August to October of last year, and that's when we could prove to ourselves that, yes, we can run 10 times faster. At that point, though, we were like, okay, how do we get the rest of the code moved? Because it's kind of painful to copy JavaScript, paste it into a Go file, and then go fix all the errors. Because there are tons of syntax errors. So what we did was we built a tool that translates at a syntax level TypeScript to Go. We obviously have a parser, and so we can walk our AST, and then we can just spit out the equivalent Go without renaming things or without changing the types. And that tool is also open source if you're interested in how we did that. Jake on our team built this. And its output looks something like this. So on your left, you see the original source code in TypeScript. And on the right, you see the translated code in Go. And you can see it's exactly the same code, but syntactic conventions have been changed. Now, you can also see there are errors in that file. That file does not compile. Because the types that it mentions don't exist and have to be refactored and blah, blah, blah. But it has no syntax errors. And so we can just then copy and paste one function at a time and then go in and fix them. And that was basically how we proceeded. So now you're going to ask, well, why didn't you just have AI do it for you? And it's not that we didn't try. But we have, AI is very good at greenfield problems where you write an English description of what you want done, and then AI spits out some code. It really is unconstrained, right? It's also pretty good at greenfields within brownfields. And what I mean by that is like adding code to your existing projects, where it has the freedom to express itself in the new code, but it has to follow conventions and so forth. But then there's like our problem, which is entirely brownfield. We want a function-to-function direct translation from TypeScript to Go. And what we want is we want a deterministic translation, not a stochastic one. And when we experimented with AI likes to hallucinate or drop a line of code here and there. So if you're doing it with AI, you got to go in and carefully check every line of code. Whereas a deterministic mapping, like the tool we built, it's a program. It's going to do the same thing every time you run it. It's actually interesting to think about like the place of languages in the AI universe, because they are basically the bridge between the stochastic world and the deterministic world, right? And often it's the case that you shouldn't ask AI to do your problem. You should ask AI to write a program that solves your problem, because then you box in the stochasticness in that program that you wrote, but when you run the program, you get deterministic results, right? Now, had AI been good enough a year ago, I mean, it's come a long way just in a year, we might have been able to have AI help us write that translator. But that's the reason we did it the way we did it. So once we had that tool, we could port binder, checker, and emitter. And at all times, we kept the code buildable and runnable. So this is the first check-in that happened in October. And there was not a whole lot going on in that compiler, but nonetheless, it was buildable, and you could run it. And it did something. And then we could gradually add more and more code by moving over more functions and adding more functionality. And that's basically how we've gotten to where we are now. We did lots of optimizing along the way. Go has an excellent profiler called pprof. Here's an example of its output looking at where are hotspots for memory allocation. And it's not surprising that the string builder, write string method down there is called a lot because the emitter emits a whole bunch of little strings, right? And so we do a whole lot of allocations there. But we found a whole lot of stuff using this tool that we could optimize, CPU-wise or memory-wise. And then finally, you know, the thing that really saved us along the way is that we have about 100,000 tests that we run the compiler through in order to validate it. And those we could simply use to validate that we are building the same compiler. In fact, I'll show you now let me go to the source code for the old compiler. And let me just try to here introduce an error in this piece of code, and you'll see that we get, you know, an error message. Let's try to compile with the old compiler. Well, actually, we don't need diagnostics here. We'll just compile it. And we get this error message. Let's try with the native compiler. We get precisely the same error message, except we just get it faster. This is what we're aiming for. Like, you won't be able to tell the difference. And the way we sort of get there is when we run our test suites, the 100,000 tests, we actually produce diff files that diff the error output of the old compiler and the new compiler and shows us for all of the ones where they differed, it generates a diff file that we can then go analyze. And we've been burning down that list of diff files and aim to get all the way down or either just say, hey, yeah, we're fine with these changes. But here's some examples of what that looks like. And you can see a lot of it is just like, how do elaborations happen? You know, but it's the same number of errors. It's just there's slight little differences that we just gradually eliminate. Okay, let's go back here. So, what were some of the challenging parts of the project? Go is obviously a much simpler language than TypeScript. In particular, I would sort of compare it to a type and memory safe C. And it's not surprising because some of the people who worked on C have worked on Go. In Go, there's no inheritance and subtyping. There are no optional properties. There are no union or intersection types. The typecasts only can happen through interfaces. So a lot of restrictions there that made it so that things that we would do in our old code base simply weren't possible. In particular, when it comes to data structures, the code is not that different. JavaScript and Go sort of have the same statements, and you know that's but the way you structure your data vastly different. And that meant we had to do extensive refactoring of all of our internal data structures, and that means like nodes and symbols and flow nodes and type objects and so forth. For example, in our abstract syntax tree, we have more than 300 different kinds of nodes. And they were all built by inheriting from a base node. And then they have a kind discriminant property, and we would use unions, discriminated unions to represent all of that. And then we would have extensive use of switch statements in the compiler. So for example, here you see the source code for the node interface, and it has a bunch of properties that are common to all nodes, and then we inherit a whole like 300 and some different interfaces from that. And then our compiler has lots of functions that look like this check expression worker here, where we then switch on the kind and then do different things. And you'll see that in some of the cases here, we have typecasts here, like node as private identifier. Now, of course, these things you don't get to do in Go. So we had an interesting challenge in mapping that world onto the Go world. This is how we ended up doing it. As I said earlier, Go has structures, structs. Everything is a struct in Go. There are no classes or objects or whatever. There are structs, and they can be allocated either on the stack or on the heap. And there's automatic escape analysis that puts stuff in the heap if you ever take the address of it, and that address survives longer than the function you're in. So nodes are represented as a node struct, and you can have pointers to nodes, so we can have references to them, right? And then we have all the common data. But then, of course, how do we then model having different kinds of nodes? We don't get to cast a star node to a star identifier. That is simply not permitted in Go. You don't get to cast pointers at all. The only way you get polymorphism is through interfaces. And interfaces are interesting in that they're sort of a deferred way of adding a vtable to a struct. Like in, say, C# or Java, or JavaScript for that matter, whenever you allocate an object, it also contains a pointer to a vtable or a type information that tells you what kind of object it is. And you pay that price no matter what. That's always part of every object. That's not the case in Go. Structs have no identifying data that says what's in them. But if you treat them as an interface, then you get a type tag and a pointer to the data. So an interface pointer is actually a fat pointer. It has two pointers in it. You know, one that's a pointer to the vtable and one that's a pointer to the data. Now the way we get there then is that we have every node contain the common data, and then we have store an interface in the node that references a sidecar with the rest of the data, like all of the stuff that's specific to identifiers. And then you're going to go, well, gosh, now you're doing 2 allocations per node. Isn't that bad? Well, no, because then we use another trick in Go, which is embedding, where we put the base node inside the more derived node, if you will, and have it point to itself. And now when you have a star node, you can get at all the common data, and then you can take the data pointer in there and cast it to what you've proven that it is, say a star identifier, and then you can get access to the rest of the data. That actually works out pretty darn well. This is sort of what it looks like in Go. Here's the node struct. And you see there's this data property, or the data field, which is an interface. And then we have helper methods that say, if you have a star node and you've proven that it's an identifier, then here's a helper when you say .as identifier that casts that data to star identifier, and now you're holding a star identifier. And then there's another one that says as node, and that goes back to the base node. And that in turn then means that we can now get the same structure of the code, and it actually performs remarkably well. Because now, in a lot of cases when we're walking over ASTs or whatever, we're just like, this is just a memory access to get the kind of the node and the common data and whatever. It's super efficient. Another interesting aspect of Go is the way that it represents strings. First of all, Go uses UTF-8 encoding instead of UTF-16. Like if you're like C#, Java, JavaScript are all UTF-16. And UTF-16 was a great idea until it wasn't. Because once we got past 64K characters, then we still had to deal with double word characters. And now you're having to decode anyway, but now you waste two bytes per character. And almost all characters in a program is ASCII. And so, 8 bits is plenty. And so in Go, you're just storing the source code takes up only half as much memory. So that sort of helps. The way Go represents strings is interesting. A string is basically a little struct that has a pointer to some bytes and a length. And so strings are, in a sense, by value. And with the zero initialized state of a string is simply an empty string. It's a null pointer, but it's also a null length, and that's valid. And so if you ask for the length of that string, it's 0. And you don't have to initialize it. It's just 0 by default. It's kind of like a memory-safe char star, if you will. And the thing that's really interesting about it is that substring is an allocation-free operation. Here's an example that I just stole from some Go documentation, where you first assign hello to a string S, and you see you get this double pointer or the double word thing that's a string, a pointer to the data, and the length 5. But then if you substring, say, go from index 2 to 3 in that string, you just get another pointer into that same byte array with a length of 1. That's an interior pointer to the data. And so Go's garbage collector supports interior pointers, meaning that even if you then forget about S, well, T is still keeping that string alive because it points into the middle of it. Now, if you think about what does a parser do in a compiler, a parser takes one big string, your source code, and makes it into a bunch of little strings, right? And builds a data structure around those strings so you can navigate around in the code and find all the identifiers and what have you, right? That basically becomes allocation free with this scheme, because substringing all of those is just, it doesn't cost anything. Another interesting trick that we do is pool allocation, and that actually takes advantage of the fact that Go permits interior pointers. So you can have an array of elements of some type, and if you have just one pointer to one of the elements, then that'll keep that entire array alive for as long as that pointer is a live root. Now, in a compiler, you allocate a lot of data of the same type. For example, 30% of all of the nodes in a program tend to be identifiers. And they're all the same kind of thing, right? And so whenever so there's an opportunity here to pool objects with the same lifetime. For example, when the parser wants to grab an identifier, well, in say C# or Java or JavaScript, we'd have to go allocate one object for every identifier, right? Well, what we do here is we allocate chunks of 256 identifiers in a pool. And then we just hand out interior pointers one at a time as we need more. And when the pool is exhausted, then we just grab another one because those pointers are going to keep that array alive. We don't even have to remember it. We just, fine, the GC will figure it out. The only thing we have to make sure is that they all have the same lifetime, because otherwise you end up wasting memory. But source files are parsed together and they all have the same lifetime. So this is effectively a trick that allows us to reduce by orders of magnitude the number of memory allocations we have to make. And that matters, especially in concurrent environments, because memory allocations are protected by synchronization locks and what have you, and it's a more expensive operation than just this. This is all local to one thread. We don't have to synchronize anything. We can just hand out the next element in an array. So that goes super fast. In fact, that is what this code looks like. We have a pool of T, and the new operation is just grab the next element. Well, first see if the length is at capacity, then go get another one. And then just hand out the address of that element, the next element, right? And that address of operator there will actually give you a pointer that then keeps this thing alive as long as that pointer is still stored somewhere. All right, now that brings me to concurrency, which is arguably the most compelling reason for us to move to native code. A former colleague of mine, Herb Sutter, wrote a paper about 20 years ago called "The Free Lunch is Over." And what he was talking about in that paper is how Moore's law is still going, but it's no longer giving us faster single-core CPUs. It's giving us more of the same kind of CPU that run at the same clock speed, but we just get more and more of them, and that's how things are going to scale in the future. And that's pretty much been true. We just get more cores now instead of faster cores. I mean, I was just reading about this latest AMD Threadripper with 96 cores and God knows how much memory, right? And I mean, it's just getting crazier and crazier. It's not uncommon in the cloud now to have 32-core machines. And when you run compute-intensive workloads like a compiler, being fast means being concurrent today. Now, certain problem classes scale, you can leave the parallelism or concurrency to the operating system, right? If you're writing a web server, fine, you could just get a core per request. Excellent. You don't have to think about concurrency as much, at least. That's not the case when you're compiling 15 million lines of code that all reference each other, and it's one big data structure you're partying on, right? So you have to bring the concurrency into your program. And that's what we're basically doing in this port. So it's important to use all cores. It's also important to be able to do work while you're waiting. Like the minute a core wants to read a file, for example, you really want to yield that core and have something else run on it until the I/O completes, and then you want to resume and keep running there. Now, Go is very good at this. They have these things called Go routines, and elsewhere in the literature, you'll probably see them referred to as green threads. They are super lightweight threads that can be multiplexed onto actual hardware OS threads. So they capture not just the execution state, but also the state of the stack. And then when you suspend a Go routine, you're basically moving it aside and then moving in another one and moving its stack to be there, and it's a point of execution, and then resuming. And these things, they're very lightweight. Now, the thing that's interesting about green threads is that they don't color your functions. And I don't know, how many of you use async await when you're writing code? Wow, there you go. Now, how many of you have gotten bitten by the fact that when you have a synchronous function, you can't call your async functions, right? Yes, all of you. That's function coloring. Only the red functions can call the blue function. Blue function can't call the red functions, That's not the case if you have lightweight threads, because everything is a thread, and you can suspend them, and so there's no difference between synchronous and asynchronous code. And we use that to great utility, because that means we can yield anywhere and do I/O anywhere without having to ensure that the entire call stack above is async, which would come at great cost, right? And then shared memory concurrency is where the game is at for us. And what I mean by shared memory concurrency is the ability for multiple threads or Go routines or whatever you want to call them to access shared pieces of memory. Now, JavaScript forbids this, and for good reason. I sometimes joke you can have concurrency or you can have mutability, but you can't have both. Because then it becomes hard to reason about, right? And shared memory concurrency is both. And it's hard to reason about, and you gotta make sure to synchronize access to your data, and you need a race detector, and you need test suites and whatever to figure it out. But if you figure it out, you can really make some inroads. I may have mentioned already, but 50% of our performance gain comes from concurrency. The other half is from native code. And honestly, I expect it to be more and more. You saw that experiment we did on a 32-core machine there. We're likely getting more like 15x on that one. The old compiler couldn't even compile it, so I don't know how many x it is, but it's definitely up there. Let me try and demo some of this a little bit here. Switch to my machine. Let's first try to compile the old compiler with the old compiler, and I'm going to do a full build and ask for diagnostics. This is our old compiler. It's about 150 50,000 lines of code. I think, oh yeah, we still have our error in there. Maybe I should just get rid of that. Here. There. All right, let's try again. Oh, no, not that. Come on, for God's sakes. There we go. This takes about, I think, if I remember, 6 or 7 seconds. Yep, 7 seconds. Now let's try to compile with Go. Ask for diagnostics. But tell it to run single-threaded, which forces us to just run a single thread instead of multi-core. And you'll see that, oh yeah, it's faster, 1.6 seconds. I mean, that's not nothing. But let's now allow it to run concurrent. And boom, it is way faster. Thank you. Let me try to go back here. Let me talk a little bit about how we do this. A compiler has these different phases of compilation: parsing, binding, checking, and emitting. And the game here, when we are moving to a concurrent execution environment, is to take advantage of concurrency in every one of these phases. And the solution kind of looks different for each phase. If we start with, how does the old compiler work? Let's say you tell it, I want to compile this source file here. What the compiler does, loads it, and then it builds a parse tree that represents it, and then it parties over the parse tree to figure out what things are you importing or referencing, and then it loads those files, build ASTs for those, and whatever, until you have the full closure of the program. And then we do a first, this all happens sequentially, one file at a time. Then we do a first pass over all of these ASTs where we build symbol tables. And again, this happens sequentially, where we attach symbols, we build a control flow graph and whatever. And now we can then create a type checker. And then we can tell that type checker one file at a time to go in and check everything in that one file sequentially, and then check the next file and so forth until we've checked everything. That's kind of how compilation works. And then if you're emitting, then the emitter will, one file at a time, erase types and emit JavaScript source files, right? Now, in the Go compiler, or in the native compiler, first of all, we parse all the files in parallel. Parsing is it's an embarrassingly parallel problem. And by that, I mean, all you're doing is loading a file and then walking over the string and building a parse tree. It is completely isolated to that file, and it doesn't touch any other memory. So we can run, if you have 32 cores, we can parse 32 files at a time and just build the state in memory. And then because we have shared memory concurrency, we can actually reference all of these later. We can treat them as being immutable and reference them later from another Go routine that does type checking, for example, right? So we do all of that in parallel. The same with binding, where we build symbol tables, all done in parallel because it's, again, completely local to each file. But then when it comes time to check, it's a little harder, because if you think of what does a type checker do? It walks over all of these ASTs. But when you import in one file from another file, it has to sort of go visit that file and start resolving types over there, and then that might in turn refresh. And so it sort of jumps around all over this gigantic data structure that's your program, right? One way we could have solved the problem is let's go in and make all the symbol tables protected by synchronization and whatever, and try to have multiple Go routines partying on the same data structure. That probably we would never succeed. What we do instead, though, is we take advantage of the fact that our type checker is also very lazy, because it's a language service as well. And it doesn't have to check everything. It is perfectly happy to only check one file out of a program of 100 and give you only the errors for that file. That's exactly what happens in the IDE, right? So what we do to check is we create multiple type checkers depending on how many cores you have. It'll be currently is hardwired at 4, but it's not going to be the final state. And then we tell each of these type checkers about the whole program, but then we instruct them to just check a quarter of the files each. And so the first checker will sequentially check the files that are assigned to it. And the next one will sequentially check the ones that are assigned to it. They know nothing of each other's existence. It's as if you have 4 compilations going at the same time, but you don't need to synchronize anything because the AST is entirely immutable and the checkers keep their own state internally. And so they're just partying along, and it scales to as many threads as you want. And then we go in for each checker and harvest all the error messages that that checker generated, and then we deduplicate them, and that's your output of the of the compilation, if you will, which ideally is nothing. You know, that's all good compilations produce exactly nothing, right? I mean, this works remarkably well. Now, there are slight drawbacks, of course, because each checker will duplicate some work, like to resolve all the standard built-in types like array and map and all of that stuff. They all do the same work. But most of it is local to the files that they're checking. So typically we're seeing that running concurrently consumes about 20% more memory, but it goes about 3 times faster. So that is well worth 20% more memory, especially since we're still in aggregate consuming less memory than the old single-threaded JavaScript code base. This is actually the actual source code of this stuff, and it's remarkable how simple it is. Really, here's like the thing that binds all the source files. It just queues up work for each source file, and that in turn is just a Go routine, and then the scheduler in Go automatically runs them, and then we just sit and wait until they're all done. All right, so you're gonna ask, when can I use this in my projects? And I'm happy to announce today a series of native previews. It's basically nightly builds of the command line compiler and a native code language service. In fact, let me try and show you because I didn't get a chance to show you the language service in action. Here is, you can see we have enabled the preview language server. So this is the native compiler now powering when I hover. This is the native compiler coming up with all of this stuff here. I can navigate, so if I go to definition on this guy, statement completion, and you see how it is basically instantaneous. This is a 1.5 million line code source base. Also, there are, let me try to scroll up here a little bit. You see I make an error here, and you see the red squigglies appear instantaneously. In fact, I can even, just to show you how long it takes to load the Visual Studio Code project, let me try to restart the language server, and then let's count. 1, 2, 3, 4 seconds to load all of Visual Studio Code, 1.5 million lines of code, you know, and produce. Thank you. Yeah. All of this stuff is available in the native preview, and I would really encourage you to try, and then log issues if you find issues. At this point, you know, if you have single TS config projects and you're not using advanced old JS doc features, everything should work, and it should really just be a replacement, and you should be able to use it today. The language service has further to go. There are features that are not implemented yet, but you can follow along and see our progress, and we really would appreciate as much feedback as you can give us. Yeah, as I said, the command line compiler is npm installable. That's all it takes, and it lives side by side with the old compiler. And then the language service you can install from from the marketplace, and it's just an extension, and then you can toggle between that and the built-in. Some of the things we're deprecating, just so you know. In this port, we're not going to support down leveling to ECMAScript 5 anymore. I mean, ECMAScript 6 is now more than 10 years old, so I don't know of any runtimes that can't run it, so we're not going to waste the time in creating the very, very complicated state machine transforms that it takes to down-level async await to ECMAScript 5. We're getting rid of some older module targets that also, if you're using them, boy, then it's time to move on. But I don't think anyone is anymore. And some resolution modes that just no one really knows what they do. So, so we're getting rid of those. The path to completion is basically to burn down the work items. We need to port composite projects, build and watch mode, and then finish up some things like JSDoc, the emitter, the language service, and our APIs. And that's ongoing. We're hoping that by the end of the year, we're going to get close. And this will all be called TypeScript 7 when it ships. So that's when you know that we've made the move. And that's basically the end of it. I'll leave this on the slide there so you can find it. And then if anyone has questions, we got about 8 or 9 minutes here to do some Q&A. Thank you. Thanks.
Hello.
Hello.
So we, of course, all know that you did this because you want better frame rates in Doom, right?
Sure. Now you can get 1 frame per day instead of per week. Yeah.
What happens to the TypeScript compiler, the old one? It's just immediately gone after from 7 or what?
Well, I mean, so we're gonna move into. I mean, we're about to ship 5.9, so there'll be a 6.0 and maybe a 6.1 before we switch over, and that old code base is not going to go away. It's open source, you know, it'll stay there. But once we get to 7, evolution will happen in the new native code base, and we're not going to add more features to the old code base. We still have, and that was not on my slide there, we still have some work to catch up because the thing that we ported was actually a snap of 5.7 or so. Back in August or September of last year. And anything that's gone into the old compiler since, we need to backport to the new compiler. And so that's part of our work stream. But by the time we get to 7, we will be caught up, and that will then be the truth going forwards. Matt. Hi.
There was some issues with Go when it works in WASM, if I remember correctly. Because you need to run TypeScript browser for certain use cases like TypeScript Playground and things like that.
Yes.
And you mentioned, I think, at the time that there were some upstream problems in Go that you were looking at solving. I wondered if there's a status update.
Well, we talked with the Go team a week or 2 ago, and yes, they'll readily admit that WASM support could be better, and they can't do multi-threading in WASM right now, and Go is all about multitasking, right? And hopefully something will happen there. We are also looking at TinyGo, and maybe we can get that to perform. Either way, the WASM experience it's going to be good enough. It's not going to be fantastic. I mean, we found that when we can compile the new compiler to WASM. In fact, someone already did and made a playground out of it, and it runs at about the same speed as our old compiler did in JavaScript. Maybe a little bit slower, but not noticeably bad, you know. And that's perfectly fine for the playground, you know. So, yeah. Any other questions? Or you want 5 minutes back? All right, well, if you have more, I will stick around. We may have to vacate the room, but I'll be outside and we can chat more if you have more questions. So thanks for coming, and please go download it and tell us of anything you find. Thank you.